give some questions, and before I begin, I want to discuss them a little bit. So, in the last lecture, we discussed the linear dielectric material, right? Where the polarizability is proportional to is a constant, and then this capital P should be this polarization vector P is proportional to the electric field. Uh, okay, so that's by definition the linear dielectric material. And in the lecture before last lecture, we also discussed focused on the permanently polarized materials where there is an intrinsic P. And I want to emphasize today that these two materials are quite different. And so the one on the 2 lectures ago, that the polarization vector P does not depend on the external E field. So these are some special case, and this is definitely not a linear dielectric material. So when you are looking at a problem, don't be confused with 2. Even though the P is constant and uniform, doesn't mean that the underlying material is a linear and dielectric material. And next is the question about homework 1. So in homework 1, I asked you to calculate the interaction between 2 dipoles. And in the last 2 questions, I said that to apply an external E field. So the external E field, what it does is that it simply readjusts the alignment of the dipoles. So initially, the 2 dipoles are perpendicular to each other. And then you can imagine that with the external E field, the 2 dipoles will try to be aligned with the external E field. So this means that the 2 dipoles are parallel to each other instead of perpendicular to each other. So this is what the E field contributes in this problem. So it simply try to modify the configuration of the problem. And other than that, it doesn't do anything in addition. So when you are expressing the interaction, E should not participate in this expression. So in other way, you can think that initially I have 2 dipoles from home question, probably from A to E, and from H to I. You should think of 2 dipoles that's parallel to each other, but in a configuration like this. And then another is to parallel to each other, but it's head to tail. So these are the 2 configurations that I want you to calculate. Okay, so following last week's discussion, at the end of last week, we discussed the boundary conditions involving dielectric material. So we see that the V itself can be continuous. But partial V, partial N might not be continuous. So here I want to give a slightly different example. So in this example, we are considering a dielectric material below this xy plane, but on top of the xy plane, there is a charge Q. and you can imagine that if this dielectric so the distance between the charge and the plane is d. So we looked at a similar problem before. In this problem, if the bottom dielectric material is replaced by a conductor, then this is the problem of image charge. And if you still remember, the solution should be there. You can add an image charge right below this xy plane with an opposite charge. And for this, but here we are replacing the conductor by dielectric material. And in the last lecture, we discussed that the bound charge is can be defined as the and for the linear dielectric materials, the P is proportional to E, and you can immediately tell that there cannot be any volume bound charge, but there can be a surface bound charge. So the first surface bound charge is this should be. So the surface bound charge is can be written as the P dot n. And here in this problem, the surface charge should be lying on the xy plane. Now, if you calculate, because the this n vector should be perpendicular to the xy plane, so it has to be in the z-axis. So this expression should be pz, or because pz is also this is a linear dielectric material, so it has to be an epsilon naught times chi e, and times the electric field along the z direction. Now, the electric field, we can calculate the electric field. If we calculate the electric field, it must be consists of two parts. One is the electric field due to the point charge right on top, d distance above the xy plane, and another electric field is due to this surface charge distribution. So if we look at the electric field due to the point charge, then we are already very familiar with the expression. So it's minus 1 over 4 pi epsilon naught and q over r separation vector, which is these r square plus d square times cosine theta, and you can rewrite this. Oh, sorry.
You can just double tap your Apple Pencil.
Okay. So here, this is I'm expressing the Coulomb law in terms of this point charge. And this is only one contribution to the E field. And another contribution of the E field is from the bound charge itself. And but we also calculate the E field due to the bound charge, which should be below this surface. It should be epsilon b and divided by 2 epsilon naught, and that is by Gauss' law. So imagine that we've already discussed this problem before. So imagine there is a sigma b on this surface, and you can use a pillbox that a Gaussian surface like this, and slightly above and slightly below this surface. You can immediately tell that the S times twice of the S times the E field should be sigma b times the area S, whereas this E should be sigma b over 2 epsilon naught, and sorry, there is a epsilon naught here. So now, if we combine this two E fields together, and that should be giving us the total EZ. And now we replace the EZ right on above. We receive. We can arrive at the final expression of so this is the first term, and add the second term. Now, if you look at this expression contains sigma b both on the left and the right hand side. But you can solve this easily, right? So the sigma b can be solved, and it should be so now we arrived the bound charge distribution, and in principle, because we've already obtained the charge distribution, including the free charge and the bound charge, right? And then we can use Poisson's equation actually to determine the electric field everywhere, and consider that this problem is solved. And now let's take a look by actually integrating the surface charge. And if you do this integral over all space, you actually find that the charge is proportional to the original charge Q by a factor of chi e over chi e plus 2. And now if we take the limit where this linear susceptibility goes to infinite, we can see that actually that factor becomes 1. And this is actually the case of a conductor. So now this means that a conductor is really similar to a linear dielectric, where the dielectric constant is infinite. And this also actually reminds us that in the problem of the conductor case, we use the image charge to solve this problem. And in this problem, we can actually also use a similar technique. So right now, if you can see that the total charge on the surface is instead of minus q, it's a minus q times another constant. So if you want to actually use the image charge to solve this problem, then the image charge should be equal to the total charge on the boundary. So because in this case the Gauss law will be satisfied, and so if this problem can be solved by an image charge, then we know how much the total charge should be, and we actually also can guess that the image charge has to be located also at this 0 minus d, because this is the intuition from the case of a conductor, because in the if we take the E goes to infinite limits, then the image charge should be placed at 0 minus d, and it's very likely that we also need to place the image charge at the same location.
For the first appearance of sigma b, here, the first equation we have sigma b. How does that come from?
So which one? This expression?
No one.
This one.
Here.
Okay. So on the I simply use this one, right? The sigma equals epsilon naught chi e times Ez,
Yeah.
and then here this Ez consists of two terms.
Yeah.
So first is Ez due to the image charge, due to the point charge,
Yeah.
and the second is the Ez due to this surface charge itself.
Yes.
So this is the second term, and the first term is here. So I simply copied these two terms over here.
Understood.
And then this is simply solving this surface charge self-consistently. Any other questions? So now let's see if we can have actually a charge distribution that reproduce the same problem, but instead of a surface charge, we place an image charge somewhere. And now the problem here that's different from the conductor is that we have to consider the fields both above this plane, the xy plane. So above the xy plane, there is the that's our region of interest, and below this xy plane is also our region of interest. So it seems that we cannot place the image charge everywhere, right? So that's the challenging part, and how we deal with this problem is that now we still separate the problem into two parts. So instead of considering the problem all at once, we first consider the problem like here. We consider the larger than 0 case, and we also consider where we are not interested in the region below, and we also consider a case where the is actually less than 0, and we are not considering the problem over here. So for the first case, we can try to place the image charge such that it is right below this point. And for this second case, what we can do is to place the image charge right at the same spot. So now the first configuration, the image charge is, so the charge is Q and Q D, what QB, sorry. And the second one, I simply place Q and QB on the same place. Now you can easily write out this expression for the potential for the Z larger than 0. So at Z larger than 0, the V should be, so there is a first term due to the original charge. And there is also the second term due to the image charge. Now at the less than 0, since the two charges at the exact same location, then the V is actually a bit simpler. And now this is our guess of the distribution of this potential both above the plane and below the plane. And you can actually check that magically this guess actually agree with the boundary condition at the xy plane. So if you check the boundary condition, and this had to be sigma b. And now what we can claim is that we find a very particular distribution of image charge, and this solution satisfies the Poisson equation above this xy plane, and it also satisfies the Laplace equation below this xy plane. And so this solution must be able to solve the problem on both sides. And also, magically, on the edge of this problem, it also satisfies the boundary condition. Then, if this is the case, then this means that we have our problem solved. So, even though this is some kind of guess, but this guess still produce a correct solution, and because of the uniqueness theorem, then this correct solution has to be the one and the only solution. So alternatively, you can try to derive the E field from the charge distribution alone, but that derivation might be a bit difficult. So if you calculate the force between the dielectric material and the point charge, then you have to use the vector field in the above figure where the image charge is below this xy plane. So the force should simply be q times qb divided by twice of this separation vector d squared and times the 1/4 pi epsilon naught. Okay, let's check another example.
Can I raise a question? Can I raise a question?
Yeah.
So is the because the set higher than zero, larger than zero is for the test charge on like above the surface, right? Or is it on the surface? Because we're talking about the image charge. I don't know which case.
Yeah, so if we calculate the force, the image charge should be below the surface.
Yeah.
Because we are interested in the field produced above the surface, right?
So the set larger than zero is for the test charge or the image charge?
Region of interest.
Yeah.
Oh, okay.
Sorry, this QD should be QB. So now let's take another look at another problem. So here we are trying to have a conducting sphere, and it's embedded in a dielectric material, and the nice property is that this one straight goes through the center of this conducting sphere, and you will see that because it goes right through the center of this conducting sphere, this problem has the azimuthal symmetry, and if you define the origin at the center, then you can use spherical coordinate to solve this problem. So for this kind of system, we can immediately write down the general solution, that it should be a sum over all these L's, and it should be A times R to the L plus B. And now we can check the boundary conditions.
Professor, I actually have a suggestion. If you find writing on that iPod is so difficult, you can just write on the referral and take photo and upload it.
Okay.
I mean, you can voice it on the referral. I mean, the voice directly.
Okay.
So you don't need to deal with this.
Yeah.
Problem.
Yes. Someone may still looking at the online videos.
I think is that camera working? Is it a camera?
Yes, but this quality is not quite high.
Okay.
I'll try to see if I can actually work this on a different iPad. Okay. So let's check the boundary conditions. So at r equals so this problem is slightly different comparing to the problem before that. We actually consider this the surface of this conductor to be charged to be V naught, and now in this system we can try to apply this boundary conditions. So we immediately see that because the solution goes to r goes to infinite, so then this means that here this AL must go to all zero, because otherwise it will diverge, and so the problem only remains is for the B. And now for the B coefficient, we simply write down the and we can arrive at the different boundary condition for both B naught and B L. So for L equals 0, it's non-zero, but for when L is not 0, you can actually see that it has to be 0, because on the right hand side we don't see any theta dependence. So then this means that this VR theta should be actually a very simple solution, simply decays as 1 over r. And now we can also calculate the electric field, and it must be a negative gradient of this B. So is 1 over r squared, and it's along the r height direction. So this looks like a simple point charge problem, and the difference is that right now we have this linear dielectric material. So below this surface there must be some polarization, and this polarization vector is an epsilon naught times the and chi e times the electric field, because this is linear. And now we plug everything in. So from this p vector we can actually then calculate the bound charge, and both for the bound volume charge and the bound surface charge. So for the bound volume charge, And here I want to rewrite this p vector. Now, if you do the calculation, you can see that the bound volume charge should be 0, and so what's left over is only the bound surface charge, and here the only surface is the surface of the conductor, so there will be a bound surface charge on the of the dielectric material near this conductor, and if you calculate this p dot n, where this n is simply the r hat direction, and in spherical coordinate, this n is parallel to this r hat direction, so the bound charge is simply negative epsilon naught chi e v naught over r, where we simply replace this p. We replace the little r by this capital R.